Perfect. So thank you very much, Tao, for the introduction, and welcome everyone to this presentation. So my name is Kim Hammar, and I am a PhD student here at KTH University in Stockholm, where we just had Kwan Yan visit us for a month or so, and he invited me to this presentation. So so this is joint work also together with my supervisor, Professor Stadler at KTH, and the presentation will be about intrusion response through optimal stopping. So we consider the following use case. We assume that we have an IT infrastructure that you see here to the right, which consists of a set of connected components that jointly provide a set of services to a client population. And this infrastructure is managed or operated by some organization, which we refer to as the defender. So the defender can defend this infrastructure by a combination of monitoring the network to detect possible attacks and also actively making decisions to either prevent future attacks from happening or responding to ongoing attacks. In addition, we assume that there is an attacker that seeks to intrude on the infrastructure and wants to compromise a specific set of components. To achieve this, the attacker uses reconnaissance to gather information and discover vulnerabilities, and then it has to exploit those vulnerabilities in order to gain access. Okay, and we studied this use case from the defender's perspective. So you see the defender down here. It observes this infrastructure through a set of metrics, and these metrics are observed sequentially. So you can think about this as an observation process, a stochastic process. And while observing this process, at each time step, the defender has to make a decision whether it should continue to monitor the process or stop and take a defensive action. And it also has to decide which defensive action to take. So we formulate this problem mathematically from the defender's perspective as an optimal stopping problem. More concretely, the defender, while observing this observation process, at some unknown point in time, we assume an intrusion event will occur. So we don't know when this will happen, but we assume throughout the lifetime of this organization, at some point in time, an intrusion will happen. And once this event has occurred, the defender can respond to the intrusion by taking stop actions. Each stop action is associated with a defensive command and has some cost. And the final stop action is assumed to shut down the entire infrastructure. So the optimal stopping problem here from the defender's perspective is to decide the optimal times to take these stop actions in order to respond to the intrusion. And the challenge here is that you do not want to stop too early, because then you may deny service to your clients unnecessarily. And also you do not want to stop too late, because then you give the attacker a longer chance to compromise components. We can also turn the perspective around and think about this problem from the attacker's perspective. So the attacker is then controlling when this intrusion point will occur. And we can think about this as two stop actions also from the attacker's perspective. So the first stop action of the attacker decides when the intrusion should start, and the second determines when the intrusion should end. And this means that the optimal stopping problem from the attacker's point of view is to decide when to intrude on the infrastructure in order to minimize the risk of getting detected while maximizing the potential damage to the infrastructure. And if we now consider these two stopping problems jointly, then we have a game, a so-called stopping game, and it's also known as a Dunkin game after Russian mathematician Dunkin that studied this problem in the 70s. So then both players are jointly then trying to decide strategically on their stopping times in order to meet the corresponding objectives. So this is the game that we will analyze in this presentation and go into much more detail mathematically. But before I do that, I just want to give you an overview of the basic solution approach that we're using to solve this game, which can be understood on a very high level through the following picture. So the starting point here is that we have some target infrastructure, and this is the infrastructure that we assume that we want to defend. So this is where the attacker is trying to intrude. Now, typically this corresponds to either a production environment or a safety critical system of some sort. So for obvious reasons, we generally cannot run experiments directly on this infrastructure. And to get around that, we instead take the configuration of this infrastructure and emulate that in our emulation system. So this gives us a virtualized replica of the real system, a so-called digital twin, where we can run experiments, we can collect data, and we can evaluate defender strategies. And we can do this in a safe environment without, endangering the real system. And we use this data that we collect from here to perform system identification and to identify the unknown parameters of this game theoretic model. So in our case, this typically corresponds to the observation distribution of the defender. So what kind of alerts does the defender observe? These type of distributions we can estimate through system identification. And once we have done that, we can instantiate this Dunkin game and run simulations and then optimize defender strategies using numerical methods. So for example, reinforcement learning, but also dynamic programming or computational game theory. Then we take the learned strategies from this simulation, extract them, and evaluate them again in the digital twin. And if this evaluation is deemed successful, we may also implement the strategies in the target infrastructure. So that is the overall method that we are following. And in this presentation, I'm going to focus mostly on the upper parts here. So focus mostly on the theory, on the formal model, and on the reinforcement learning part. And I will de-emphasize a little bit the digital twin and the target infrastructure. So just before I move on into the more theory side of this presentation, are there any questions at this point? Also, feel free to stop me at any time if there are any questions or some clarification.
Yeah, sure. So everybody is encouraged to interrupt any time using your unmute button. All right.
Good. Okay, so this is the outline for the remainder of the talk. So far, I just covered the general use case and our approach. And next, I will go into some theoretical background on the definition of the optimal stopping problem and also formulating the game mathematically. Then we will see how we can use that game and analyze it to derive that the optimal strategies for the defender and for the attacker has a certain structure. And then we will note that given that we know this structure about the optimal strategies, we can then design efficient algorithms for computing the optimal strategies. So we'll see one algorithm for computing best responses and one algorithm for approximating an equilibrium of the game. And finally, I will then show some evaluation results where we take the learned strategies and we run them in a real system and evaluate them. And then I will conclude and provide some directions for future research. So optimal stopping is a very classical problem in statistics that has been studied for a very long time. It was actually originally studied in the context of gambling in the 18th century, where statisticians wanted to know if you go to the casino and you start gamble, then when is the optimal time to stop if you want to maximize your expected fortune when you leave the casino? But the general theory was not formalized until 1947 by Abraham Wald, that you see here on the picture. And he formalized the theory not in terms of gambling, but in terms of hypothesis testing. So if you have an hypothesis and you're collecting samples, how many samples do you need to collect before you can stop and either reject or accept this hypothesis? And since then, the theory has also been widely generalized and worked on by many people, most notably by Kolmogorov and his students like Shiryev and Dunkin, but also by more recent scholars like Bertsekas, for example. And the basic problem is that we have a decision maker that is observing a stochastic process sequentially. And at each time step of this process, the decision maker have two options. It can either choose to stop or to continue to observe. And both of these two options are associated with some utility or some cost. And the optimal stopping problem is then to find the optimal time to stop this process in order to maximize this expression here. So formally, a optimal stopping time, tau, is a random variable that is a mapping from the events that you observe through the natural numbers. And it has to satisfy one constraint to be called a stopping time. And this is basically this causality constraint that the stopping time, if the stopping time is n, it can only depend on events that happen before time n. So it cannot depend on the future. And there are two general approaches to solve this problem and find the optimal stopping times. So one is the Markovian approach, and the other one is called the Martingale approach. So the Markovian approach is by far the most common. And in this case, we assume that the process that we're observing has the Markov property. And then we can simply treat the problem of finding a stopping time as a Markovian decision problem. So then we can apply standard results from decision theory, and we can use the Bellman equation, for example, to characterize the optimal solution. There is also an alternative characterization in the Markovian case instead of the Bellman equation, and that is that the optimal value function is known to be the minimal excessive majorant. So we say that the value function is majorizing if it is greater than or equal to the stopping rewards in every state. And we say that it is excessive if it is greater than or equal to the continuation rewards, expected continuation rewards in every state. And the minimal function that is both majorizing and excessive is the optimal value function. So you can then use these two inequalities to formulate a linear program to find the optimal value function. And that is another quite common approach to solve the optimal stopping problem. The alternative approach, if you don't use the Markovian approach, is the martingale approach. And this is much less common in practice, but more general, because here we do not assume that necessarily the process have the Markov property. And this means that we cannot apply, Markov decision theory results. So in this case, rather than using, for example, the Bellman equation, we're instead using something called the Snell envelope to characterize the solution. And the Snell envelope is named after James Snell, and it corresponds to the smallest super martingale that stochastically dominates this observation process. And if you're following the martingale approach, it basically means that you're trying to find this Snell envelope, and once you have found that, then you can then derive the optimal stopping times. But in our case, and in this presentation, we're going to be in the Markovian setting. So we assume that we have the Markov property, and then we can formulate the problem from the defender's perspective, the stopping problem, as a POMDP. So this POMDP has two states, 0 and 1, where 0 means that there's no attack, no intrusion, and 1 means that there's an ongoing intrusion. The observations corresponds to IDS alerts, which are distributed according to some distribution F. This distribution is typically unknown to us. We make no assumption about this, but generally we can estimate this through system identification by collecting samples from the real system. Actions, of course, stop and continue at every time step. The reward function gives the defender a reward for maintaining service to clients and for responding to intrusions, and as well as penalties if it fails to respond or if it makes a false alarm. Transition probabilities depends on the attacker model, but it's common to assume that the intrusion start point has a geometric distribution, since that is a memoryless distribution and then satisfies the Markovian assumption. And the objective then for the defender is to find the stopping time that maximizes the expected utility over the horizon, where the horizon here is a random variable that depends on when you take the stop actions. So that's the model of the defender's optimal stopping problem. And more or less the same model is applicable for the attacker. We just turn things around. So in the attacker's case, the main difference is that it has full observability. So it, of course, knows the intrusion state. And I make this assumption also that the attacker can infer the observations of the defender. So the attacker is aware that if it launches an attack, this will generate a certain amount of alerts for the defender. So therefore, the attacker is sort of intelligent and aware of the belief that the defender will have. And so this is then an MDP rather than a POMDP for the attacker's stopping problem. And if we now consider these two stopping problems jointly, we can then formulate this as a one-sided partially observed stochastic game. So we have two players. Player 1 is the defender and player 2 is the attacker. And player 1 here then has partial observability, whereas the attacker, player 2, has full observability, we assume. And in this presentation and in our previous work, we have assumed that a zero-sum setting. So making it simple for us, we assume a zero-sum game. And this is something we may extend in future work to drop this assumption. But we assume zero-sum, so the defender is maximizing and the attacker is minimizing. So that is the formal game model that we will analyze. And we will try now to derive certain results regarding the structure of the optimal strategies for the attacker and for the defender. So this is the main result we will focus on, and that is that given a fixed attacker opponent, then the best response strategy of the defender corresponds to an optimal policy in a POMDP. And this POMDP has the following properties. So the first one is that the stopping sets, so the subsets of the belief space where it is optimal to stop, they have this nested structure. So here L corresponds to the number of stops that the defender has remaining. So what this says intuitively is that the fewer stops you have left, the more conservative you want to be with your stop action. So if you have only one stop action left, then you have the smallest stopping set. If you have many stop actions left, then you have much larger stopping set. Second, if you only have one stop action remaining, then there always exists a threshold, alpha, and an optimal threshold policy of the defender that takes a stop action whenever the belief exceeds the corresponding threshold. And we can then also generalize this. So if you have more than one stop action remaining, then, and if you make this additional assumption that the observation distribution is totally positive of order 2, and I will get back to this condition later on. But if you assume this additional condition, then there exists L thresholds, so one threshold per stop action, and these thresholds are decreasing in L. And there exists an optimal multi-threshold policy for the defender that selects or takes a stop action whenever the belief exceeds the corresponding threshold. So this is quite a mouthful, this theorem, but actually it's very intuitive. And I think when I visualize it to you, it will become quite clear. So we consider here, this is our belief space from 0 to 1 of the defender. And 0 means that the defender knows that there's no intrusion. 1 means that the defender knows that there is an ongoing intrusion. And everything in between, we have uncertainty. So what the theorem says is that if you only have one stop action remaining, then there exists a thresholding point here, alpha, such that everything above that threshold is in the stopping set. And if you have more than one stop remaining, say 2, then there's another threshold, alpha 2, that is going to be less than or equal to the first threshold. And everything above that is in a stopping set. And this theory then applies inductively for all L. So if you have L different stop actions, then you have L different thresholds, and they are decreasing in L. And the stopping sets have this nested structure, as you can see, where S1 is a subset of S2, S2 is a subset of S3, and so forth. So what does this mean then in terms of our use case, intrusion response? Well, it basically means that if you have an intrusion response system that is receiving alerts from a intrusion detection system, then the optimal thing to do is to keep updating the belief with these new alerts until your belief reaches the corresponding thresholding points. And then you should take this automated response action. And this is quite interesting because one, this is a very interpretable policy. So, and the second thing is that it's very easy also to implement this policy in a real system, as we will see later. So it's quite a attractive result, I would say. So,
yeah. So sorry, quick question, Kim. So the threshold results we're talking about right now, does it only apply to POM DP setting, the one decision-making setting, or applies to actually game setting, the POSG?
Good point. So it applies to the POSG in the sense from a best response. So the best response strategy is when you fix the opponent, then basically it reduces to a POM DP, and then the threshold result holds. But in the equilibrium, then we do not have the threshold properties. So in the equilibrium, then the defender cannot follow like this kind of deterministic thresholding strategy. It has to have a different strategy. So this is only for the best response for the defender. It does not apply to the equilibrium strategy.
I see. Okay, I see. Yeah, maybe we can talk about your equilibrium later when we discuss them. All right, because I want to take a look at how you define your equilibrium.
Yeah, all right, absolutely.
Okay.
Thank you. Okay, so the next, basically what I want to do now is basically give you an idea just behind the proof of this result. And so the next maybe 10-15 slides will be quite dry with maths, but I will try to give you just the main idea. And if you cannot follow all details, I think that's just normal. So, but I'll try to keep it clear. So the first lemma we're going to use is just this very well-known result that the optimal value function is piecewise linear and convex. That has been known in a POM DP, that is, which has been known for like 30-40 years and was discovered originally by Sondic. So in the POM DP setting, the challenge is that we're no longer working just with a fixed or discrete state space. Rather, we have this continuous space of beliefs that reside in some unit simplex. And this raises some concerns related to how do we represent the policy and how do we represent the value function, because they are now mappings from continuous domains. So but it turns out that in practice, even though we have in principle an infinite set of beliefs, in practice, there's only a finite set of belief points that we can actually reach from any initial belief. And the way I like to think about this is that you can always convert the POM DP as an extensive form game against nature, where nature is deciding your observations. And then if the POM DP is finite, then this extensive form game will have a finite set of pure strategies. And this means that for each pure strategy, there's a finite set of belief points that you can actually reach. And since the set of pure strategy is also finite, then there's a finite set of belief points in total that can be reached. So if you consider this example here, this is also called a conditional plan in the POMDP literature. So it's just a pure strategy in this extensive form game. It says that in the initial belief, we select action 1, then nature will respond with an observation. And based on that observation, our strategy will select the next action. So clearly here, if you follow this strategy and say the game ends here, there's only a handful of beliefs that you can actually reach, depending on what the nature responds. And based on this knowledge, we can define the value function of the belief as follows. So we can enumerate all of these conditional plans, the pure strategies in this extensive form game. And for each such conditional plan, we can define a vector alpha that is a vector of the length of the state space that contains the value of following this conditional plan in each state. So the expected reward following this conditional plan in each initial state. And then we just define the value function of the belief, when you don't know the state, as the dot product between the belief and the alpha vector, which clearly is a linear function in the belief. So here we have examples of 5 different conditional plans or pure strategies. So we have 5 different linear functions. And here I just assume a 2-dimensional state space so I can plot it. But the theory applies also if you have arbitrary state space. And then, since this is just a linear function, the value of a given belief or given conditional plan, then the optimal value function is just going to be a maximum over a set of linear functions. So that's going to be piecewise linear and convex, or concave if you're minimizing. So it's going to be just the upper surface of these linear functions here. So that's quite an elegant result, in my opinion, and turns out to be a very practical result as well, because we're going to use this when we do, for example, dynamic programming and any kind of computation. Then this is how we represent the value function, just by having these alpha vectors. And then for an arbitrary belief, to get the optimal value, we just take the dot product and the maximum between the belief and the alpha vectors. So the next lemma we're going to use is that the stopping set, when you only have one stop remaining, is convex. And so what we want to show now is that if you have 2 beliefs, B1 and B2, that are in the stopping set, then any convex combination of B1 and B2 is also in the stopping set. Okay? And first we just use this lemma we just saw, that the optimal value function is convex. It is piecewise linear and convex. So this inequality holds by convexity. Second, we note by assumption B1 and B2 are in the stopping set. So we can replace the occurrences of the value function for these 2 beliefs with the Q factors, right? Just by definition, since it's optimal to stop in these beliefs. And then if you look at this convexity inequality for the value function, we can rewrite it in terms of the Q factors, the right-hand side. And now, since we assume here that there's only one stop action remaining for the defender, it means that when the defender takes this stop action, the game actually ends, or the POMDP ends, it terminates. So we can actually rewrite these Q factors just in terms of the reward function. So first I write it in terms of the reward function of the beliefs, and that is just the weighted sum of the reward function in terms of the state. And this expression here turns out to actually be the Q factor of the convex combination of B1 and B2. And that is by optimality less than or equal to the value function of the convex combination. So we have shown now that this Q factor is less than or equal to the value function and also greater than or equal. So we have equality. And therefore, it is optimal to stop also in the convex combination of B1 and B2 if B1 and B2 are in the stopping set. So we arrived then at the result that the stopping set is convex because for any 2 beliefs in the set, the convex combination is also in the set. So we have basically shown this part of the result, that the stopping set, when you have one stop remaining, is a convex set. And what remains to show now is that beta has to be equal to 1. Because right now we don't have this threshold structure that we want, because now you need both the lower threshold alpha and the upper threshold. But we want to show now that belief, so the beta is necessarily going to be 1, and therefore you only need to know alpha. And this is also very intuitive if you think about our application domain. So belief of 1 means that we know that there's an ongoing intrusion. And clearly you want to stop if there is an intrusion. So this is just what we're going to show mathematically, that if there is an intrusion, you always want to stop. Therefore, 1 is also always in the stopping set. And therefore, beta has to be 1 always. And to show this, we simply plug in 1 in the Bellman equation, and then we also plug in our reward function, and then we just obtain directly that the maximizing action is S, so it's a stop action. Therefore, the belief equals to 1 is always in the stopping set. And then we obtain this result that if you only have 1 stop action, then there always exists this thresholding point, and the optimal strategy or policy is to stop whenever the belief exceeds this threshold. So we have shown this part of the theorem. Now the next thing is to show that how we can generalize this if you have more than 1 stop action. So this is the next step. But maybe I can pause here just if there were something unclear about this first part of the result.
A quick question, Kim. So of course you have showed us one approach to prove this result, and I was thinking about apply the standard argument from the Krishnamurti book. You have also listed here. So what if I just show that the policy is monotonic with respect to the maximum likelihood ratio on the belief space? Can also prove that this is like a partition or is a threshold form, and because there are only 2 actions, stop and continue. So, the 1 or the beta star has to be 1. How about that?
Yeah, that's a good point. I think there are many ways to prove this first one. And you're right that you can use I'm not sure if you need to have any other additional assumption if you prove that the policy is monotone using the maximum likelihood order, but you can definitely, if you prove that it's monotone, then this result follows. So you're right about that. And I think my proof here is kind of a little bit specific as well, because I just use my definition of the reward function and plug it in, but you may have some more general proof actually.
That's true. Yeah, thank you very much.
Okay, so the next result is just to show that we're going to show this result that the stopping sets have this nested structure. So if you recall, I said before that this just means that the fewer stop actions you have left, the more conservative you want to be with the stop. So if there's optimal to stop in some belief when you have L stops remaining, it's always going to be optimal to stop also if you have more than L stops remaining. So if you have L plus 1. So first we note just from the Bellman equation that it is optimal to stop in some belief if and only if this inequality holds. So the idea behind the proof then is to show that if this inequality holds for some belief and some L, so L stops remaining, then it will also hold for the same belief if you have L or more stops remaining. Okay, and we're going to show this by first just showing that this is non-decreasing in L, and that the right-hand side is non-increasing in L. So this is our left-hand side. That is simple because that follows directly from the way we define the reward function in this stopping problem. To show the right-hand side is a little bit more tricky since it involves the belief updates. And we're going to do that using an induction argument. And we're going to use a common trick here that we do induction on the steps of value iteration. So we know the value iteration converges in this particular POM P. And therefore, if you can show that this expression here is a non-increasing in L for every step of value iteration, then we'll also hold for the optimal value function. And that's what we're going to do. So just for simplicity of notation here, we define a function W to be this difference, so from concise notation. And we initialize W to be 0. And then it follows that the base case of the induction holds. And then we make the induction hypothesis here that this difference here is non-negative for some iteration k-1 of the algorithm. And then we will show that then it must also hold or be non-negative for iteration k. So if we just expand this difference of W in terms of the value functions, and then we can expand it once more in terms of the Bellman equations for these value functions, and then we obtain this expression here. So we see that this depends on several actions. It depends on the action you take when you have L stops remaining, L minus 1 and L minus 2. So we basically have to go through all of these cases and a combination of these actions and show that in each case, this expression here is non-negative. And there are 4 cases we have to consider. So we have stop, stop, stop. All actions are in the stopping sets. Then we have stop, continue, continue. And then we have stop, stop, continue, and then continue, continue, continue. And it's basically just go through each of them and show that this expression here is non-negative. So the first one is the simplest one. When you have all the stop actions, then this actually becomes directly the induction hypothesis, which we assume is non-negative. In the two other cases, then you can obtain a little bit more tricky expressions, but then you can invoke the Bellman equation to show that this has to be non-negative, because otherwise it wouldn't be otherwise the belief wouldn't be in this have these set memberships here. So you can use the set memberships here of the belief to then use the Bellman equation to show that it has to be non-negative. And the same thing goes for the third case. In this scenario, we also apply the Bellman equation to show non-negative. And in the last case, when you have three actions of the same type all continue, then again the induction hypothesis applies directly, because you obtain exactly this expression. So then what we have shown is that the stopping sets have this nested structure, and we're almost there now with the final result. But there's one thing missing, and that is that we still allow this scenario here. So now S1 is a subset of S2, but S2 is not connected. So we could have had this scenario, and then we wouldn't have this threshold structure that we want. So the final thing to show is that the sets here must be connected as well. Okay, and the idea behind showing this, in our case at least, is that we're just going to show that if there is some belief in a stopping set B, and then we have some B prime that is larger than B, then B prime has to be in a stopping set as well. So again, we use the Bellman equations to state that if B is in a stopping set, then this inequality holds. And then we're going to show that if this inequality holds for some B, then it will hold also for some B prime, if B prime is greater than B. And here is the technical, the thing about the main technical thing about this proof. And then we're going to utilize this this lemma from the book that you mentioned, that if you have two beliefs and they are ordered, and you have this additional assumption that the transition and the observation probabilities are TP2, then this the order between the beliefs is preserved through the update of the beliefs. So through the Bayesian filter, when we update the beliefs for a new observation, the order is preserved. And this is a lemma that we're going to use. I'm just going to clarify this, because this is kind of new terminology. I think this is the first time I read about this, at least, so maybe it's first time for you as well, about this totally positive of order 2. And it basically means that if you have a stochastic matrix, a row stochastic matrix, then the rows are ordered according to a stochastic dominance order, where the final row is the largest in this order. And an equivalent condition is that all the second order minors of the matrix are non-negative. So second order minor corresponds to the determinants of the 2x2 submatrix. So in this example, we have a 3x3 matrix, and it then has 9 minors. And to show that this one is TP2, we have to show that all of these 9 minors are non-negative. Another technicality here is that some authors define TP2 to be that the minors have to be positive, and others define them to be non-negative. And I'm going here with the non-negative because this is what is used in the exact lemma that we are using. But anyway, so this assumption we make, so by definition, our transition probability satisfies TP2, and we make the assumption that the observation matrix also satisfies it. But we also actually have some empirical data that like supporting this assumption, because in practice, on our real system, we do find that the matrix is more or less TP2 in practice. We find that when you do it on the real system, we have like millions of minors, and out of those million minors, there's maybe 3 or 4 that are negative, and remaining of them are non-negative. Okay, so anyway, if we use that lemma, then the only thing we need to show that the stopping sets are connected is that this expression in red here is weakly increasing in the belief. And I'm not going to bore you that much with this, because it's exactly the same proof idea as we had in the previous one, that we apply induction on value iteration. So we make an induction assumption here. Then we want to show that this implies that it holds also for k. So we assume it holds for k minus 1, and then we want to show it holds for k. And just like before, there are a few actions here that are involved. So we have to go through each case of these actions and show that in each case it holds. And in our case, it does. So, but this is quite trivial to just go through each case and verify that indeed it is weakly increasing in the belief. And then, so showing now that the stopping sets are connected, then we finally arrive at our desired result here that...
Sorry. Just a quick question. I got a little bit confused. So before this connected thing, we have proved some sets are convex, right? Is the same set we're talking about, the S set,
Yeah, that's a good point. That's a good point. So we proved that the that S1 is convex. So yes, the
S1.
first.
Oh,
Yeah. So the convexity holds only if you have one stop action.
oh,
If
okay.
you have more, unfortunately, then the sets are not necessarily convex, and this is we cannot show, but we can instead show that they are connected.
Oh, I see. Thank you.
But it's true, if you just remain in the regime where you have one stop action, then you don't need to show connectedness because it follows from convexity.
Yeah, that's what I mean. Yeah.
Okay, so yeah, that was the main results from the defender's perspective. So if you have a static attacker opponent, not a game theoretic setting now, just a static attacker opponent, then the best response have this particular structure. And we can do a very similar reasoning about the attacker. So if you have a fixed defender opponent, then almost by the same reasoning, we can show that the optimal stopping strategy for the attacker also has a threshold structure. The main difference being that the attacker, since the attacker is not aware of the state of the game, the attacker can condition his strategy on the state, which means that we have more thresholds. We have twice the number of thresholds. So you have L thresholds per state. And that's the main difference from the attacker's point of view. So I'm not going to go through that proof because it's very similar. And it's also available in our paper if you want to have a look. So that kind of concludes this analysis of the structure of the best response strategies. And yeah, you mentioned also about I didn't have this in the slides, but about what we define to be an equilibrium of the game. So we consider here a partially observed stochastic game, one-sided. And this game we can prove always has a mixed equilibrium, but it doesn't necessarily have a pure equilibrium. So in the equilibrium, two pure threshold strategies will not be an equilibrium in our case. So but what we're going to do instead is that we're going to utilize this structure of the best response strategies to basically use them to approximate an equilibrium through a fictitious self-play process. But did you have a question about that?
Oh, so my first question is that what are the equilibria you're considering? It is a Nash or Stackelberg?
Okay, good point. Yeah, we consider Nash equilibrium.
Nash.
So, yeah.
So give me a second. Okay, if you're considering Nash, then there is a okay, so here's my understanding. So if you're considering Stackelberg, it feels like the I mean, who moves the defender? The defender is partially observable, right? The defender. Okay, so defender commits to a strategy and a Bayesian update. I mean, Bayesian belief update, so that for the attacker, it becomes a MDP, belief MDP.
Yeah.
And the defender is dealing with a partially observable MDP. That is okay to me. But if you're saying you're talking about Nash, then basically there is no commitment. So there might be some signaling effect in the play, meaning that let me rephrase my thing here. So here's because let's talk about the algorithm. I think the algorithm may review something. So say if you're using dynamical programming to find the strategy, you'd go backwards, and the operator you apply should be interchangeable. I mean, argmin, argmax, the min-max should be interchangeable.
Yeah.
And you can claim that, oh, that is a Nash because, you know, min-max is interchangeable. If it is not, you can only apply, for example, you can only apply first, say max, then min, and the two cannot be interchangeable, then I would say it may be Stackelberg instead. So then going back to your algorithm, do you prove that interchangeability of your, you know, the operators that you consider in your dynamical programming?
Yeah, good point. So yeah, so we have not considered I will get back to the algorithm, but we're also starting with the Stackelberg thing. So we have not considered the Stackelberg case, but I think if you consider Stackelberg, then probably you can obtain even nicer theory, because then
easier.
You have one moving at each time step, and you don't have this that both move at the same time. And then you can probably show that even in the equilibrium, you may have some more thresholding structure. But in our case, we have assumed this Nash setting where both move at the same time, and the proof, just to start with that. So the proof about the equilibrium that we're using is based on this one-sided partially observed stochastic game. And the way they prove that the equilibrium, the Nash exists, is that they show basically that if you have a infinite horizon, but you have a discount factor less than 1, then there's a finite approximation of that game as an extensive form. And then they invoke extensive form theory to show that an equilibrium exists. And regarding the dynamic programming, so we have not, in our case, we have not presented a new dynamic programming algorithm. We just invoke this heuristic search value iteration algorithm. But I believe in that case, they do prove something similar to what you were talking about with the operators and things. But
I get your point. But yeah, so another comment is that if we're talking about this heuristic value iteration, then my point is that they're using Stackelberg actually. They didn't prove the interchangeability of min max or max min. They just say, inf and sup, and that is fixed. And then they prove that exists, and the algorithm, will sort of works. So that we can talk about it more maybe later.
I'm not sure if we talk about exactly the same thing, but I think, I will look into it today. But basically, we only use that one as a baseline in our case to basically show that we applied their algorithm to our case, but it's not the one we are using actually. So, but we can go back to that later. Yeah. So, okay, so now knowing just that these threshold structures exist, we can utilize that knowledge to compute both the best responses, and we can approximate the equilibrium more efficiently. Basically, we don't need to consider this huge strategy space. We can just reduce it to much smaller ones. And if we start with learning the best response, so if you assume a static opponent, then we can simply parameterize the strategies with threshold vectors and initialize them randomly. And then we can update these thresholds through simulations by stochastic approximation, right? So in our case, we parameterize the strategies with these smooth threshold strategies. Then we estimate the gradients using SPSA, and then we iteratively update the thresholds following the gradients. But in principle here, you can use any black box optimization. You can use Bayesian optimization also to just estimate what are the optimal thresholds. And the way we approximate an equilibrium in this game is simply to utilize this knowledge that we can compute best responses efficiently. And we just approximate the equilibrium here by basically creating a fictitious self-play process where we iteratively compute best responses, and then we average them to converge towards a mixed equilibrium where we basically randomize over all the previous best response strategies through a classical fictitious self-play process. So this has nothing, we don't use any fancy dynamic programming here. We have just utilized quite a basic fictitious self-play process. And then when we evaluate this, compared to standard algorithms, by no surprise, then basically by utilizing this knowledge about the threshold structure, we can converge much quicker. So if you look at the upper plot, then we compare our algorithm for learning best responses against some state-of-the-art algorithms. So we compare against PPO as a reinforcement learning algorithm, Shiriev's algorithm for change detection, and HSVI for POMDP. And all of these algorithms eventually converge towards the optimal or best response strategies, but we can see that our algorithm tends to converge much faster to a close approximation of the optimum. And then when we do the evaluation with the equilibrium, then we compare mostly against NFSPs, which is another fictitious self-play algorithm for this type of game. So near fictitious self-play, so it's basically a deep reinforcement learning algorithm. And the same thing here, that we converge closer to the equilibrium much faster, but also NFSP eventually converges towards the equilibrium. And then we cannot do a direct comparison against HSVI, which is the algorithm that Bosansky and those have developed, since they only compute the value function. They don't compute actually the equilibrium strategies in their algorithm. But we just showed there how long time does it take to converge to a close approximation of the optimal value function or optimal value of the game using HSVI. And then we can see that actually, in their case, this is a surprise to me that their algorithm is actually very efficient. So I was expecting our algorithm to be much faster than this algorithm, which has much stronger theoretical guarantees, but they're actually quite fast as well in getting a good approximation of the optimal value function. And this is basically acknowledgements to the group in Czech, because they basically gave us the code to use this as a baseline. Okay, so that is basically the algorithms that we have been using for learning the best responses and the approximating an equilibrium of the game. And we can maybe discuss this afterwards as well in more detail. But as a final note, I just wanted to show also a little bit of practical evaluation. So when we take these strategies that we have learned now in the simulation, can we run them in a real system and see some results? So if you recall the slide I had in the beginning, our approach for evaluation is that we take the configuration of the target infrastructure, and then we basically use that to create a digital twin of the infrastructure. So we essentially replicate the relevant functionality of the real system in a virtual environment. So in our case, this is exactly the target infrastructure we have considered. It consists of about 30 components. And to create this digital twin, we first take each physical component here, and we emulate that with a Docker container. Then we take all of these services and the vulnerabilities and the operating systems, and we emulate that with software running inside the containers. We achieve isolation between the containers and resource constraints using standard modules in the kernel. We emulate arrivals from this client population here using a stationary Poisson process. And finally, we emulate the network conditions based on previous empirical studies of these kinds of network. So basically, previous studies of enterprise networks. And following these steps, then we obtain this digital environment that we can use to collect data and to evaluate strategies. And we can do all of this without affecting the performance of the underlying target infrastructure. So we then use the data we collect from here to do the system identification part. And in our stopping game, the only thing we have to identify is what are the distribution of the observations for the defender. Okay, and there are two distributions. So we have one distribution during normal operation and one distribution during intrusion. So the red one here is during normal operation, and the blue one is during an attack. And we estimate these as Gaussian mixtures that we compute with expectation maximization. So what you can notice that they have quite a lot of overlap, these distributions, but we also note that the bottom distribution has much more probability density at the larger values of the number of alerts. And once we have then estimated this distribution, then we can instantiate our game and run simulations and optimize defender strategies and evaluate it. So here, I'm not going to go into detail on this, but we can just focus on the leftmost column and the reward. And we evaluate then the learned defender strategy here against a static opponent in simulation and in the digital twin. So in the simulation here is in red, and the blue curve shows the performance in the digital twin. Okay. And what we can note is that the strategies converge to close to optimal quite quickly, but that is not so interesting. I think the interesting thing here for us at least is that the difference between the red and blue curve, there's a difference. So this performs a little bit better in simulation, but the difference is not so large. And this is the encouraging thing for us, because if we just ran this in simulation, we really would have no idea if this actually worked on a practical system. But through a lot of trial and error, we eventually got something that is quite robust and actually works quite well also in the real or in the digital twin environment in blue. So that is quite encouraging for us. And even though these policies are still very restricted, of course, it's just a stopping strategy. So there's a lot of assumptions, but given these assumptions, it tends to work quite well in the real environment. So to conclude this presentation, in our research, we're trying to develop a method to learn effective security strategies for complicated IT infrastructures and complicated cyber attacks. We have applied this method to an intrusion response use case, and we have shown that under certain assumptions, we can learn effective strategies for a practical system. We have also developed a theoretical framework around all of this based on optimal stopping theory, and we have demonstrated that this theory gives us quite a lot of interesting insight about the solution. And we've also utilized that insight to design efficient algorithms. In future work, we want to extend this in many ways. So I think the main line of work for us is that we want to close the gap to reality. So we have currently quite a few assumptions still, and we should see how can we generalize that and make it more realistic. That's the main goal for us. Then there's also quite a lot of interesting theoretical work that could be done. And you mentioned, for example, stackable game, and that's not something we have worked on, but I think it will be very interesting for someone else to have a look at that problem. So thank you very much for listening, and I'm happy to stay on for discussion and more questions.
Thank you very much, Kim. Thank you. So now this is the Q&A session. So maybe we can start with myself. So I have a question about the digital twin, basically the last few slides in your presentation. So maybe the number one question is, what do you think of the difference between, say, digital twin and vanilla simulation? Say I build a simulator, and
Yeah.
I can also claim that this is a digital twin. So what do you think of the difference? Do you see there is a difference or not?
So in principle, I mean, if you do a very good system identification here, then there shouldn't be a huge difference, because if you manage to estimate these distributions that you really need to do the simulation, like the distribution of observations, then there's not a big difference. There doesn't have to be a big difference, at least. But I think it's you really need to have some way to verify this. You need to have this digital twin just to provide the data to instrument your simulation to ensure that the difference is small. If you don't do this instrumentation, then it's very likely, I think, that your simulation will be quite different than the real system. But if you have some way to, identify the unknown things from your simulation based on some more realistic data, then the difference doesn't have to be very large.
I see. Then the follow-up question is that, do you see any difference between building a digital twin and building a simulation? Because either of them requires, say, data from your real system, requires, say, for example, system identification. So do you see any difference building, those two items?
Yeah, so I would say, I mean, it's quite a huge difference. So this one, if you look at the gap, compared to a real system, the gap between a digital twin and a target infrastructure, if you go look here, I think this gap is not very large, because it's quite, you really replicate functionality from the real system. You run the real operating system, you run the real services, you replicate the software running here is exactly the same as in the target infrastructure, but the hardware is different. Right. Whereas when you do the simulation, then it's quite a big difference. And regarding the development, my own experience is that, I mean, developing the simulation of a Markov game, that takes, an hour to do in Python. Just if you have the functions already, just implement them in Python. It's not a huge engineering effort. But building a digital twin is quite a big engineering effort, since you need to automate all of this process of spinning up the containers, connecting them in virtual networks, starting the services, emulating the client population, and so forth. So regarding engineering effort, is quite a big difference. Yeah.
I see. And also, speaking of this engineering aspect, when we are building a digital twin, do we have to deal with this hardware aspect, or it's also purely software based, like writing Python? That's all.
Yeah, so it's purely software based, and also it uses virtualization technologies to abstract the hardware. So in our case, we do not have we run. So look, when I generate this digital twin, I run it maybe with 30 Docker containers, and all of these containers run on the same physical host. So I do not try to emulate the hardware. And some reviewers, they try to be picky and they say, well, the hardware, you don't replicate the hardware. And that's true. So one assumption here is that we do not try to study hardware attacks. So if you can make that assumption, then I think you're fine dealing no hardware at all. Just try to do everything in virtualization. Yeah.
I see. And also maybe one final question is about the 3-layer figure. I mean, you have simulation, digital twin, and the real system. Yeah. So from your figure, I can tell that the say difference between your simulation and say digital twin is controllable, is minus, let's say. And is that what we mean by the figure, right?
Yes, it's basically controllable in the sense that you can do the system identification to kind of close this gap. But my own experience, however, is that it's still quite a little bit of, first time you do the simulation, typically the difference between them is quite large. And then you see, okay, my digital twin my simulation didn't pick up on these details in the digital twin. And then you tweak the simulation to make it better. And eventually you end up with something that's very similar. Yeah.
I see. So yeah, that's actually what our question is. So we have a gap between digital twin and simulation, and we also have a gap between digital twin and the real system.
Yeah.
Right. So I wonder, maybe we can say, because digital twin can also be, sort of experimented. So we can somehow manage the first gap between simulation and digital twin. Regarding the second gap between digital twin and the real system, maybe, I'm not sure what's your opinion. Maybe it's beyond, I mean.
Yeah, that's the thing.
Yeah.
So usually I get questions quite a lot. So like, how do you verify that digital twin is actually replicating the real system? But this is something that I would love to try to verify this. But I mean, this is generally not possible, because this entails that you would have some real operator, maybe Ericsson, and they will tell you, okay, you can run your reinforcement learning agent on our real system. And we are very far from that being accepted, in an operational environment. So I think the best we can do right now is something like a digital twin. And then as this technology matures, then maybe we will be able to do kind of field studies where we can actually try on a real target infrastructure and then verify the gap. Yeah.
Thank you. Thank you very much.
Thank you.
Any questions?
Yes, I have a follow-up.
Yeah, please. Maybe you can come here. Yeah, we have a follow-up question. Please wait up first. Yeah, you can take us.
Hi, thank you, Kim. Thank you first for your nice presentations. I have a quick question as for your experiment settings. So because here you mentioned that you have a digital twin and then you do simulations and then you implement these strategies. I wonder how you abstract your the attacker and the followers strategy from the digital twin in this reinforcement learning. Because in the learning, the action is very abstract, is just attack or not attack. But in order to map this strategy to the digital twin, we have to do some modification, right? I'm just wondering how you deal with this details.
Yeah, that's a good question. So can I start by explaining how it works in a digital twin? So in this case, we typically define a time step in the Markov game to be 30 seconds. So in each 30 seconds, we run an attacker command like a port scan, and we run a defender command. And then we let the 30 seconds go, and then we measure all of the metrics that we need, like the IDS alert, for example, and then we can update the belief state and whatnot, and then we can sample the next action and run that in digital twin. And we keep doing this in time steps of 30 seconds in a digital twin. The difference when we do it in the simulation is just that then the actions are vertical in the sense that nothing happens when you take the action. We just sample when the attacker takes the action. We just sample from the corresponding distribution if the action was executed during an attack or during no attack. So in the simulation, everything is, like you say, abstracted up, and all actions are vertical in the sense that they don't have any real effect on the system. We just basically know that, okay, we take this action, we have some logic that designs, okay, which distribution should we sample from in our model. That's the only thing that happens when you take the action in the simulation. Whereas when you take the action here, we actually run, a bash script that runs the action, and then we read out the observation through a measurement. So that's the main difference.
I see. Thank you. So in that case, so you don't really consider about how should I say? So let's say if I am an attacker, maybe I can launch different attacks, attack different nodes, and these attacks sometimes can be quite different and result in different consequences. But here we don't consider it, right?
Yeah, so that's actually something we're working on currently, but in this particular work, we make a very big simplification that we just assume you have a binary state space. Either there's an attack, or there's no attack. We don't differentiate between stages of attack. We don't differentiate between types of attack. Also, we don't differentiate between like configuration of the infrastructure, because maybe a defensive action will also change the configuration, like deploy a honeypot or migrate a node to some zone. All of these details about the state of the infrastructure, we abstract away, and we just have a binary state space, intrusion or no intrusion. So when you try to do this more realistically, like we're trying to do now with the future work, is that then you have to model the state space much more detailed, and then the belief space blows up usually, and things becomes more complicated. But that's something we're working on currently. But in this work, we keep it simple. Yeah.
Yes, I see. Thank you. Because I know making the system more realistic is really a very challenging work, especially it requires a lot of engineering effort.
Indeed.
Yes, thank you.
Thank you.
Any other questions?
So maybe I can.
Okay, you can share it.
Use mine.
Yeah, okay.
Yeah, I can use mine. That's good. Okay.
Yeah, that's all right.
Okay, it's good. Yeah, I think it's a quite a Can you hear me?
Yes, I hear you. Hello.
Can you hear me? Oh, can you hear me?
I can hear you.
Oh, good. So I think it's a quite interesting. I think it's a lot of endeavor here, right? Because I think it's for people to do that research. I think you have to read a lot of things, and including dynamic games, and not just games, but dynamic games, and Palm DP and stochastic games and stopping time. There's a lot of literature you have to go through, and also at the same time, we have to also look into how to really make it work in practice. I think it's to do this research is is a remarkable amount of effort that is going behind it, and yeah, I can for people who don't see that type of effort. It's a lot of effort, not just reading one paper and you can just start to do research. Especially it's a collection of readings and a collection of learning materials and a collection of background, I would say, in order to embark on this endeavor. So maybe let me start with as a simple question. I mean, I start with like a application question first. So what is your state space here in the digital twin? I'm assuming that it is a abstraction of the real. I mean, if you go back to the real network, you could have states, right? Okay, each machine, each server might have a state. But when you look in the digital twin, do you have an abstraction of these states or aggregation of these states or equivalence of some states? So what is how you define a state in your model, in your abstraction?
Yeah, that's a good question. So like I say, in this work, we have basically done huge abstraction, just consider a binary state space. So either there's an attack or not. But in the digital twin and in our current work, we're trying to extend this. Then the way we define a state is basically that each node will have a bunch of states, and typically not that many states per node. This can maybe 10 states. And states could be, for example, corresponding to which zone in the network is the node. Is it in a DMZ, or is it in a production environment, or is it in some research development zone? And it could also be corresponding to what is the intrusion state of this node. So the attacker may have compromised some nodes and not some other nodes. And that gives you maybe 10, 15 states per node in the system. And then you have maybe 30 nodes, and then the complete state space is then the configuration of all of these nodes. In our case, we do not model the state of the edges in the graph, so the communication links. We assume them to be fixed.
Mm-hmm. So in other words, this is a way to avoid because if I have a state for each node and there is a linkages connections between nodes between different nodes, then it's easily to go to state explosion, right? Because you can, I mean, there's so many states, and we're gonna go into the classical, like say, challenge of computation. But instead, I mean, I try to abstract something out of that complication. I think that's an interesting approach, I would say. It's a sort of it's just an effective modeling, right? It's not like try to say, okay, what exactly my circuit is really try to understand, okay, what is the thing that I want to what is, effectively speaking, what is behavior, right? Not try to model the white box, not try to model the white box, but maybe like not exactly the black box, is sort of like a little bit gray box in the middle.
Yeah, I think you're absolutely right. And like I say, the problem here is just that this combinatorial explosion and the curse of dimensionality. So one other thing we're looking into now that you can exploit here is that maybe you can have a local policy per node, and that local policy will then have very small state space per node. And then you can exploit symmetry across the nodes. So maybe you can have the same local policy for every node that takes local actions, and then you have a global coordinator somehow that works on an abstracted state space, something like that.
Right. Yeah, I think that's good. I think there's a lot of ways to maybe a lot of ideas as well to make it useful, right? I think probably could be context driven and application driven. I think that's great. And the second is going back to your theory. I think you're looking for stopping time, and so my question would be: are you looking for are these best response, or are you looking for equilibrium? Because I think what you have probably like presented the results there. Am I understanding correctly? It is like, say, suppose I fix what attacker does, and this is what is my stopping time policy should be. Am I correct?
Yeah, you're absolutely correct, Kwanyan. So basically, I can say that we have basically no insight really, in our case at least, I don't have it, any insight about the structure of the equilibrium strategies. We only have insight about the structure of the best responses when you fix the opponent. In our case, maybe someone more clever than me will find some structure in the equilibrium, like we were talking about the Stackelberg approach, maybe that could lead some more structure on the equilibrium. But in our case, we have only shown structure on the best response.
I see. So what is interesting? You know, I can point you to some old papers actually. What in order to solve the Nash equilibrium or for a saddle point equilibrium in zero-sum game in this case, I think that the way to do it is that you need to look at a subgame, and for each subgame, it is let's just do a thought experiment here. Think about last stage of the game, right? So, and then you're going to have a matrix game, right? For matrix game, then you can look into stochastic stopping time problem. You know, in other words, what's the probability for it to stop? Instead of saying, okay, instead of like just looking at threshold policies, but you're going to have at every step, you're going to have a probability of stopping. So this is going to be a way to look into this Nash equilibrium. In other words, you're going to extend from a stopping time policy from pure ones to stochastic ones.
Yeah, that sounds like indeed a good approach. So you mean then that the action space maybe of both players is just a probability from 0 to 1, and they have continuous action spaces, basically moving that probability around.
Yes. So instead of saying that, okay, I have a stopping time, like a deterministic stopping time, like say to go or not to go, right? But because thinking about it, because if you do that, then it is a one-person problem. Because if you have a two-person problem, then you have a matrix, right? So in other words, like say you can go and I can not go. You can stop, I can go, and the other person can stop, the other person can go. Then you have a matrix. Then it's not very clear whether there's equilibrium, right? Because I mean, pure equilibrium exists or not. It's not clear. Of course, if you're lucky, then there's a pure one. But usually you have to go to the mixed strategies.
Yeah, indeed. And exactly in our case, especially, it's very clear because you see if the defender has a threshold strategy and we assume that the attacker has complete observability, so you have one-sided game, then the attacker is trivial. It can just, if the belief is below the threshold, then attack, otherwise just wait. I mean,
yeah. So of course, I mean, there are assumptions where we can impose where you know, there existence of a pure strategy. For example, if your game happens to be submodular or some structure on top of that, then yes, there's a pure strategy. If we do that type of analysis, then your current result will actually hold perfectly also for that type of games. So I think there is a way. I mean, I can send you some. I mean, I did some papers that extend the analysis into a mixed strategies, right, versus just a pure strategy of stopping and to stop or to continue.
Yeah, that would be very helpful. Thank you. And also, just one question for you. So, what do you think about what is the most suited like equilibrium type in this kind? I've used Nash equilibrium here, but you see other equilibrium types like subgame, perfect, or you mentioned Stackelberg, or what do you think about this thing?
Well, actually, I mean, it's what you do here is, you know, different people have different opinions. From my opinion, this is a saddle point equilibrium because you're looking at a zero-sum game, and a saddle point in B in a belief space, state space, right? In a belief space. So this is it's actually it's a saddle point equilibrium because it's a max-min problem. And that's good. It's good to start with a max-min problem. Actually, this is my, if you want to look at it, maybe it's also Stackelberg game, because if you just see it as max-min, it's actually Stackelberg game, right? I mean, if somebody is doing max, the person doing min, right? I mean, that's just a different way of looking at it, unless they don't have the same objective. The max player has a different objective from the min player. Then you're going to have the Stackelberg game. So this is what I see. But I think what is important is that I think what people looking here is time consistent or sub-game perfect type of equilibrium, because you're looking to every time you look at B, right? Starting with a belief, and your policy is a function of belief. right? Statistics. So
Yeah.
this is what I think is interesting. And also what is also interesting is this, because this is related to your later context of emulation or digital twin. So if you can actually abstract, like say something, like you actually can define your own state space. Here's my thought. So why don't we just define everything over the observation space? Because if this is something that you can observe, right? Like say I only can observe something. Why? Of course, I can define a hidden state space somewhere, but because I'm doing digital twin anyway, right? I can define any state space I want. It's not like I have to really infer some true state, because this state is what I call it. It's my creation. It's my construction, abstraction anyway. So I mean, my point is that why we need to go to the complication of creating a partial observable problem, unless this partial observable problem, I'm really observing the thing I'm trying to infer is the real state, right?
Yeah. I think I didn't think about it like that, but I think there is a lot of merit to that idea, because the more you can measure from the real system, the better. So if you can somehow define the state space also over the observations, then, and you can easily measure them, then I think everything becomes simpler in this mapping between emulation and simulation.
Right. But of course there might be a reason, right? Because that depends on how we're going to create this digital twin. Because we can always create, like say, a Markov chain just over the observational space, right? Yeah. My battery is going to die. But my last point is that I'm thinking right now we don't have any like a penalty on how many observations we want to observe, like with the observation cost, because I think in a lot of applications, because in cybersecurity, I mean, observing something could be very costly, and if we want to create some cost in that, maybe also to be very helpful for us to decide. I mean, maybe that's could a component that could be introduced, especially we don't expect this process is going to go to infinite, right? Because usually people make decisions quickly, and there's a trade-off of acquiring some observation at the same time making quick decisions, right? So, but of course these are further extensions, yeah, I think I mean there's a lot of interesting ideas. I mean, actually, one thing I want to also argue that there is a relevance of this problem to not exactly the same, but to something called inspection games. Of course, this is not exactly in the same form, but there is a connection, because it's about, like, say, inspection game means that, okay, suppose I can give you like a 10, like say there is a patroller, and he can only inspect 5 times out of 10. And so how he can allocate, these, when he should patrol, basically over the span of 10, times, right? Yeah. So this is also something that it's relevant, but it's not exactly the same problem. And then also maybe I should stop here. But another thing I would really like to understand, or really will be very interesting, is the topology. So, because I think one problem is really exciting about this networking problem is really the topology. I think this is some constraints of a topology, how that the topology is going to enter this into this stopping time problem, right? If that, of course, that probably will rely on the abstraction of the digital twin, and what type of topology helps, what a topology does not help. How we can leverage the topology, I especially because it's a networking problem, right? And I really like to bring that into our context. Maybe the topology will help us to make some good assumptions about what type of game we are playing. Also, anyway, these are just. I have so many thoughts, but we can talk about it another time.
Thank you very much, Kwon. It's a lot of very good ideas. And just about that with costly observations, I think also I've thought about that. And I think there is some interesting stopping theory about these extensions, but many good ideas there. Yeah.
So maybe we should go back to Tao's computer, because my computer is dying. So let's go back to his.
All right. Okay, any other questions?
Yes, here. Yes. Can you hear me?
Yeah.
Yeah, probably have to. Yes, my question would be, so if I'm understanding correctly, if you have like L actions of stopping, then you basically, by studying this structure of optimal stopping policy, you basically construct a policy that is like more general, using the threshold policy, using like L different threshold policy, right? That's the essence of it, if I'm understanding correctly.
Yeah, that's correct. And basically you can think about it in a nested way as well. So if you have multiple stops, then when you have taken all your stops, you only have one stop left. Then you're back at the original optimal stopping with just one stop. So yeah, that's basically how they are related.
So that type of special structure of this policy basically encapsulates the say dynamic property of this problem. Is that correct? Otherwise, it's just like a static problem. If you have to define just one stop action. Otherwise, it's just a static problem.
Yeah, no,
Okay.
exactly. It captures the dynamics of the problem. And I think this, if you look at it from the use case perspective, it makes most sense. If you have multiple stops, then you should assume basically that the first stop you take is maybe the least conservative. So if, as a defender, you maybe start by just turning on deep packet inspection, maybe. Then the next action, maybe you shut down some part of some service. And you go so on, like more conservative actions, where the final one is to shut down the entire infrastructure. So
Yeah.
it basically captures that structure about the thresholds, that they are, you start with a very low threshold, then you take the first action, then for the next one, you want a higher threshold, because now you're going to do a more severe action as a defender.
So if you take a holistic view of this policy structure, basically you have bypassed the whatever is dynamic in this problem, like signaling scheme, or whether it's Stegelberg or Nash. That's why you said this is Nash, because you have characterized this optimal policy by taking a holistic view of this entire horizon. I don't know if I'm expressing it correctly, but in my opinion, basically, after you characterize this optimal policy, you don't have to consider whether it's Nash or Stegelberg or not. This is just a follow-up of Tal's question, but it's just in my opinion. All right.
Yeah. Okay, to continue.
Yeah. Yeah, that's just a little comment. But my question would be, what because you have characterized the structure of the policy, then what has led you to the specific choice of this function parameterization? Because I've seen you using a very specific threshold policy here, 1 plus blah 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 to the power of -20 blah blah blah, and then because in reinforcement learning it makes a difference if you choose different like function parameterization, right? Because it's deep learning essentially. And have you tried also what has led you to the specific choice of like the gradient estimator? Because I've seen you have different like algorithms like PPO, et cetera. I wonder if you're using the same kind of function parameterization in other algorithms, or just more general different policies.
Yeah, I would say that we have done basically very little, like we've not been exhaustive at all here. We just basically started with this, and it tends to work very well for our case with the SPSA estimator and this parameterization. But in principle, I think I'm pretty sure there are other parameterizations and other black box optimization techniques that will work better. I think, for example, that Bayesian optimization would be very interesting. But regarding the parameterization, the reason we did with this was just that we wanted to use SPSA, and we wanted to use the stochastic approximation theorem that it should converge. And then we needed the function to be differentiable, the threshold strategy. So we couldn't have just a hard threshold, and then we just parameterize it with this soft threshold. And then with this parameters of this soft, you can control how steep the softness should be as well. So that's basically the reason, but we actually did not really spend that much time on it. So I think there's a lot of opportunity to check other parameterizations and other gradient estimators. Yeah.
I see. Because I've seen in your figures, you have different converges, like the cumulative reward might be different for different algorithms. So I wonder if that plays a factor in this. So yeah.
I haven't investigated, but I think that can very well be the case indeed.
Yeah. Thank you.
Thank you.
Yeah, all right. Any other questions? We're good. Okay. Yeah, thank you very much, Kim. Thanks for the great presentations. And I'll get you back later. All right.
I think Kim probably will be coming to New York one day, right?
Yeah.
Yes, I'm very happy to
I think
come
maybe
visit
planning
someday
to
soon.
Here, probably in May or something.
Oh, we can meet in person actually.
Yeah.
Right.
Yeah. So hopefully, next time will be in
Okay,
person.
and let's
thank you very much.
say thank you very much, and maybe have a good night, Kim. All right.
Thank you, and you have a good
Okay.
See you
lunch.
next time.
See you next time.
See you next time. Bye.